Nicky Maga from BAC 1B. I will discuss is all about carbonate equilibria in natural water. Natural water, which include the ocean and freshwater, lake, ponds, and streams, act as a major interface between the lithosphere and the atmosphere, and also between this environmental compartment and much of the biosphere. In particular, the ocean with its large volume serves as both a major reservoir for a number of chemical species, and the deep ocean current also provide an efficient mechanism for the long-distance transport of substance. Although it is commonly stated that the composition of natural water is controlled by a combination of geochemical and biological processes, it is also true that these processes are to some extent affected by the composition of the water. Among the parameters of water composition, few are more important than the pH and the alkalinity. The latter affect the degree to which water are buffered against changes in the pH, and it also has some influence on the complexing of certain trace cation. Natural water contains a variety of weak acid and bases, which include the major element present in living organisms. By far the most important of these carbon is the form of CO2, HCO-3, and the CO2-3. The carbonate system, which the major source of buffering in the ocean and is the main subject of this chapter. The carbonate system encompasses virtually all of the environmental compartment, the atmosphere, hydrosphere, biosphere, and as CaCO3 major part of the lithosphere. The complementary process of photosynthesis and respiration drive a global cycle in which carbon passes slowly between the atmosphere and the lithosphere, and more rapidly between the atmosphere and the ocean.
The dissolution of limestone, calcium carbonate. At low pH, we can view the dissolution reaction as a reaction between calcium carbonate and hydrogen ions to produce free calcium ions and carbonic acid. And at intermediate pH, we can see the dissolution as a reaction between calcium carbonate and free CO2 and water to produce calcium ions and bicarbonate. And at high pH values, we can view it as a very simple relationship between solid calcium carbonate, free calcium, and carbonate ions. And this way of viewing the calcium carbonate dissolution is consistent with the previous discussion about which inorganic carbon compounds that dominate at different pH values. The equilibrium equation is written very simply as a solubility product, that is, the product of the concentration of calcium ions and carbonate ions. And the dissolution equilibrium constant is about 10 to minus 8.4. Here I want to make a disclaimer. At high concentrations of ions, we should actually use the activities rather than the concentration. But for this analysis, let's stick to the simplification that the activity equals the concentration. Now we need to look at how the ANC can be defined. As shown in previous episodes, the charge balance states that the sum of the anions to the strong acids and the anions to the weak acids must balance the cations to the strong bases and the cations to the weak bases. And this results in two different definitions of the acid neutralizing capacity, the ANC. One is the difference between the anions to the weak acids minus the cations to the weak bases, and the other one is the cations to the strong bases minus the anions to the strong acids. However, if calcium carbonate is present, the calcium ion is in fact cation to a weak base, and that means that we need to change in the upper definition to include calcium, and correspondingly we need to remove calcium from the second definition so that the calcium ion is no longer considered as a cation to a strong base, but rather the cation to a weak base. And here we have the same definition of the ANC. As you may recall, to calculate the relation between the ANC and the pH, we need to substitute all these concentrations for expressions where the H plus I is the only variable. In this case, the equations we need to use are the solubility product of calcium carbonate, but that can be written as calcium 2 plus equals the ratio between the solubility constant and the carbonate. And before, we have developed an expression for the carbonate concentration as a series of constants times the carbon dioxide pressure divided by H plus squared. And we can combine the last two expressions to get an expression for the calcium 2 plus concentration as a product of the solubility constant times H plus squared divided by a series of constants and the carbon dioxide pressure. To make the calculation, the equation we have to solve is A and C equals and a series of expressions, where the first one represents the OH concentration, the second one the bicarbonate concentration, the third one the carbonate concentration, the fourth one R minus, then we have H plus, aluminum 3 plus, and finally the calcium concentration. In terms of numerical calculations, what we actually have to find is the root to the equation 0 equal minus A and C plus the various terms that come from the charge balance. And whoops, it appears as I forgot a 2 in front of the carbonate concentrations in both equations. So let's look at the solution to this equation. Here I have made a series of calculations of pH as a function of A and C in the water. And the calculations have been made for a certain DOC value, ambient carbon dioxide pressure, and at a certain temperature. And the red curve represents the pH as a function of A and C without any calcium carbonate present. However, if calcium carbonate is present, we see that the pH will be higher, especially at low A and C value. And that is because calcium carbonate acts as a solid base that dissolves and thereby consumes H plus ions. Now we can relate these calculations to the data that we have looked upon earlier.